When developer write software, they don't write binary. They write code in languages like C, Java, or Python. But your CPU understands only one thing, and that is machine instructions. So how does human readable code become something CPU can execute? That transformation is what we are exploring today. Software starts as source code. This is code written by humans, and this is readable for humans, but meaningless for the CPU. If you see this code snippet, int a equal to 5, int b equal to 10, int c equal to a plus b. So a person who don't know programming, that also will be able to read, like there is a variable a, something called b, and now c is addition of a plus b. But CPU does not understand this. To run this code, we need something called a compiler. A compiler translates this source code into machine instruction that CPU can understand. It converts human logic into CPU instructions. Before machine code, there is often an intermediate representation also, which is called assembly language. The thing which you can see in this screen, move A to 5, move B to 10, add A and B. So this is simple, the assembly instruction of the previous program that we have seen. Yeah, this one. So assembly is also a human readable form of CPU instructions. So if you want to see which type of instruction that CPU execute, you can see here. These are the instructions that CPU execute, and human also can read it. But each assembly instruction usually maps to a real CPU instruction that we cannot read, and that is not at all human readable. And then comes machine code, and this is what the CPU actually executes. And these instructions are represented in binary, all 0101 or something like that. To the CPU, everything is just numbers. Now, once the code becomes machine instruction, it is stored as an executable file. So whenever you run any program, so then one file is getting created, let's say program.exe. So that is executable file. And when you run the program, the operating system loads it into the RAM. So as we have learned previously also. So this executable file in the storage it's nothing but a collection of bytes, but it will become program and it will get executed once it will be loaded into RAM. Then only CPU will take instructions from it, right? And the CPU begins executing those instructions using the instruction cycle we discussed earlier: fetch, decode, and execute. So some languages work slightly differently, like Python, JavaScript. Instead of compiling directly into the machine code, they are executed by an interpreter or virtual machine. But in the end, everything still becomes CPU instruction. But the intermediary part may change for some languages. Now, attackers usually don't look at the original source code. They analyze compiled programs, right? Because that is going to run in your devices. And there are some terms with which they are able to analyze these compiled program. Something we call reverse engineering, malware analysis, exploit development. And that means they study the machine instructions the CPU actually runs. So the journey looks like this. From source code, it goes to compiler. Then it goes to assembly to change in that assembly level code, which is also human readable, similar to CPU instructions. Then machine code, where the exactly CPU instructions come, everything 0101. And then executable file, and then it goes into RAM. It loaded into RAM from our storage, and then from RAM, instructions by instruction getting executed in CPU in the instruction cycle we have learned. So this is the whole flow of a program that is sitting in your storage. Every program you run is just a machine instruction being executed billions of times per second. In the next video, we will explore something very important for cybersecurity, and that is endianness. How computers store numbers in memory and why it matters. We'll discuss it all. And remember, we'll keep it simple.